Bem-vindos to one more episode of the Type Theory for All podcast. As always, this is your host, Pedro Abreu. And today is my great pleasure to partner with Serokell to bring you this conversation with Vladislav Zavialov. Serokell works on software projects that require deep technical research, strong engineering judgment, and high-performance architecture. The team focuses on complex problems where standard development approaches are not enough. Vladislav, in particular, he works at Serokell doing some very serious Haskell. For example, he's one of the main contributors of the GHC for quite some years now, and he has been a member of the Haskell Steering Committee and the current implementer of Dependent Haskell. In this episode, our conversation talks about the development process of the GHC. He explains with details how the decision process of the community to modify the language works through the Haskell Steering Committee. And I must say that we get pretty technical discussing the GHC internals. He basically gives us a class of how things look like internally and how can a newcomer start hacking the GHC today. Finally, we also go into details into the theory and implementation of Dependent Haskell. If you enjoy the show, please don't forget to show your appreciation by becoming a patron or through one-off donations or sponsoring episodes like this one. Visit typetheoryforall.com to find all the details available. So without further ado, let's get into this episode. All right, welcome everyone to one more episode of the Type Theory for All podcast. As always, this is your host, Pedro Abreu, and today I have the great pleasure to have Vladislav Zavialov from Serokell. Did I get your name mildly correct?
It's good enough, thank you.
So tell us, Vlad. So you work at Serokell, and I was, you work a lot on the GHC and working on dependent types and all of that. I'm very curious to hear a little bit more about your background and how you got involved into these projects.
Yeah, well, you know how the saying goes that a blacksmith makes his own tools. That's also true of programmers. We write our own libraries and we can contribute to the compilers for the languages that we use, and somehow this line of thinking led me to writing over a dozen GHC proposals, 250 GHC commits, and I also served a 3-year term on the GHC Steering Committee. And well, my general interest in programming language just started as a teenager. Some 15 years ago, I decided to make my own video games, as all teenagers do. And I didn't know how to do it, so I thought, all right, I'll write my own game engine. And for that, I need my own scripting language. And to this day, I'm still stuck on that first step of making a scripting language. Forget the game engine. I'm just trying to make a language now. And of course, the most challenging part of that is designing a language that would actually be good, that would feel nice to use. And I've no idea how to design a good language, so I decided to read some literature. I went down the OOP rabbit hole, learned everything about the design patterns and stuff like that. Then I've discovered there are other programming paradigms, and functional programming in particular caught my interest because I like the idea of immutable data, pure functions, domain modeling with some types. It's all very nice techniques to write code with fewer bugs. And I had this idea, perhaps a subconscious idea, that I needed to learn every language feature. So I've read the entire GHC's user's guide, or rather its section on language extensions, and it was more interesting to me than actually making software. And once I've run out of features that are implemented at GHC, I needed my fix. I started reading about the more theoretical ones, so I started reading papers, PLT papers. I couldn't understand most of those papers, but I could read the abstracts, and those were very compelling. So I thought to myself, all those papers look so good, and the ideas are so interesting. So I wish I could understand more of what's written in the technical sections of those papers, rather than just the abstracts. And I couldn't find a better way to do that than to just get my hands dirty and start hacking, to do some compiler engineering. And in my free time, I'm writing toy compilers, and at work, I'm trying to contribute to GHC, all with this background goal of getting back to making my own language someday in the future. Maybe never, but who knows.
So you decided to never actually go to the university and like have some formal training.
Yeah, in the university there are many courses, and I was interested in nothing but compiler engineering and PLT. So I decided, well, the literature I could get it online. I could study it myself. There is no problem with that. So I just skipped as many steps as possible and just tried to find a job that pays and is generally aligned with my interests.
That is incredible, actually, because I don't know, these things are already hard enough, let alone learning yourself. You make it even harder, I think. I'm always surprised to see people who can teach themselves, like programming languages theory and things like that. So do you understand the papers now? Or do you still feel like you struggle with it?
I understand like I went from understanding the abstracts to understanding about 50% of the papers, which is good enough to allow me move forward with the actual implementations.
Yes, for sure. That's awesome. That's really, really incredible. And how did you end up at Serokell? Was that your first job, actually?
No, my first job was backend development in Haskell. I did it for a couple of years. And then a friend who worked at Serokell told me that I should try working at this company because it's got great culture, remote work, and stuff like that. And yeah, he was right. I joined Serokell and never looked back.
That's awesome. And it does sound like a pretty cool company. Can you tell us more about it? The kind of work that Serokell do, and how is it internally?
Yeah. So Serokell works with other clients, and we develop custom-made software for them, mostly in Haskell, sometimes in other languages, mostly functional languages. So it's Haskell and OCaml. If we are doing formal verification, we did some projects in Agda. We try to do infrastructure using similar technologies, so it's Nix. And we're also doing Rust lately because it also has a very interesting type system which could be applied to solve real-world problems. So its borrow checker, I find it very impressive.
And what kind of clients do you guys have or aim to?
I think that somebody else at the company would be better suited to answer that because I mainly focus on GHC. I've been very lucky that Serokell decided to invest into researching how to improve Haskell, and this created a position for me, which just at that time of my life, I was trying to find ways to combine my personal interests in compiler engineering with having a job. And this position at Serokell was created by me talking to the management and saying, this could be a nice idea to contribute to GHC directly. And I said, yeah, it is a nice idea. And that's what we've been doing.
It's awesome. I'm always impressed, how sometimes, we're able to find ourselves, this perfect position, and people are willing to hear our crazy ideas and make them work and work with them, right? So is that how you ended up being part, finding yourself part of the, how's it called? There's a committee to accept pull requests for
the GHC Steering Committee.
Yes.
Yeah. Well, initially I was only submitting proposals to the committee and then implementing them. And over time, I've got a good feel for what the process is like. And I thought, okay, I'll try to apply as a committee member. It was a very interesting experience, but it is a very difficult volunteer work. So after my first 3-year term, I decided this was my contribution. I'll get back to writing code because serving on the committee, it means you are dealing with other people's ideas, which might be very much outside your area of expertise, but you still need to give useful feedback to those proposal authors. And that means that in order to write like one paragraph or a response 1 paragraph long, you have to study many sources to actually understand what the proposal is even about. It's similar to the papers. I can understand the abstract, but here I have to comment on the actual technical merits of the proposal, and that involves a lot of technical detail. So after dealing with like 3 or 5 proposals, I've realized that it is very time-consuming. I no longer ever complain where the committee takes too long to respond. Because previously, as the proposal author, I found that annoying, and now it's perfectly understandable. Maybe next year they'll get to it.
That is awesome. That is awesome. I have no idea how hard. Like I think I can understand why it's so time consuming and hard. But it's always nice to hear the actual experience. Because we don't know how is it like behind the scenes, right? For example, I think that's very similar also to the process of submitting a paper as well. The reviewers have to really understand and go in depth on the technicalities of the paper, and it's not all the time that you're able to be allocated something that is really, really in your expertise, right? And we are always kind of like super snarky as well about, this reviewer has no idea what he's talking about, but hopefully they're trying their best as well, right? It's a lot of work.
That's right. And I think that GHC Steering Committee, and some context for those who don't know what that is, it is a committee of people who nominate themselves from the Haskell community, and the goal is to have representation for those who teach Haskell, those who practice Haskell, those who research it. So it needs to be well-rounded. So it needs to be different people with different backgrounds. And whenever someone comes up with a change to the language, it needs to be evaluated from different perspectives, and that's where the committee steps in, and everyone brings their own perspective. So somebody cares more about backwards compatibility, somebody else cares more about the elegance of the theoretical formalism, stuff like that. So when those perspectives are combined, the proposal author gets very nice feedback on how they could improve their proposal.
How many people is the committee constituted of?
About 9 to 12 people, depending on when whose terms end.
And is there some kind of election to be chosen there?
Yeah, I think that the current committee members vote on the next committee members or something like that. I don't remember the details.
Cool. Are you still involved with the GHC community? Like being part of it inside instead of just submitting proposals?
Oh yeah, I write Haskell code every day. Sometimes it's commercial projects for the clients at Serokell, but that is only a small fraction of what I do. I'm rarely involved in that. Mostly it's working on GHC, so I'm implementing new language extensions, fixing bugs, doing refactorings. Most of my work is working on the Glasgow Haskell Compiler.
There is a difference between working and submitting pull requests and being part of the steering committee or whatever the Haskell Foundation has under the hood. Like you're not involved in that part anymore, are you?
Yeah, I would say I'm less involved now than before, because for me, the main goal was to implement dependent types in Haskell, and I actually got into this process of submitting proposals and then reviewing proposals as a way to unblock the engineering work, because the engineering work cannot start until we all agree on what we are actually trying to achieve, on what we are doing. And as soon as I've got a sufficient number of proposals accepted, by the committee that I've got now years of engineering work ahead of me. I'm focusing on that instead.
Nice. That's very cool. So yeah, so I was asking about, like you basically walked up to your boss and you convinced him that, okay, I'm going to be working on the GHC. This is going to be really good for the company, because then I'm assuming this is more or less what happened, right? Because now that you work directly on the GHC, you can push forward the direction, which is also good for the company, like implementing better things for the language that will also get it back to the company. Is that more or less the right idea of why Serokell is interested in that?
Well, I never said to my boss that it would be good for the company. I only said it would be like a nice thing to work on. And they were very open-minded about it, and they found ways how it would be good for the company.
Okay, wow, that's that's even better then.
Yeah. Serokell's success as a Haskell company, it actually relies heavily on working with the community. So we run a tech blog. I've also authored some articles on that tech blog. We also do interviews and bring well-known names into those interviews. We worked on YouTube podcasts and lectures, created the Haskell certification program that was handed over to the Haskell Foundation for further development. And we launched a shop with Haskell-themed t-shirts. So funding GHC work is just one of those activities that doesn't directly generate revenue for the company, but it helps develop the language that Serokell is built around, because we all use and love Haskell, and it's a win-win situation for both us and the community.
That's awesome. That is really, really cool.
That is also why I get to basically determine what exactly I'm working on within GHC. So it's not directly determined by the needs of any particular commercial project, but it's rather that dependent types in Haskell would be really nice. Let's work on that.
Oh yeah, let's talk about it then. Maybe before we jump into dependent Haskell, let's talk about Haskell itself. Like, let's talk about the features of Haskell that like made you maybe fall in love into it and made you want to work more deeply with it. You mentioned immutability, for example. What else?
So it's just the classic features associated with functional programming. So purity and immutable data as a way to lessen the mental burden when thinking about code. Because if you don't have mutable state and all your functions are pure, they are so much easier to test, so much easier to reason about. You can use equational reasoning and just convince yourself that your code is correct by thinking really hard about it. It's not something you can do in an imperative language. You think really hard about it and it's still wrong. But in Haskell, you go through the steps, you consider all the cases that your code is handling with pattern matching, and because it's pure, you just identify the corner cases, see that they're handled correctly, and then you have a very high level of confidence in your code. And of course, this also relies on using ADTs for domain modeling, or sometimes, if you're feeling adventurous, GADTs to prove more properties. So that's how it goes typically. You have a domain, you model it with data types, you write pure functions to manipulate those data types. Having a type system helps you. You do type-driven development, and the next puzzle piece, it falls naturally into place just from the surrounding types. And on top of that, Haskell also has lazy evaluation, which gives us the also nice reasoning properties, because you can do substitutions more freely without worrying about making the evaluation time blow up. And we've got a really nice runtime system with concurrency support, and also it's very unique in that it makes lazy evaluation, which I've just mentioned, actually practical, because the hardware isn't built for lazy evaluation, but somehow GC makes it work, and a lot of that is the runtime system.
Can you tell us more about it? how the things that make laziness feasible?
A lot of engineering work was put into it. So there are special cases in the garbage collector, for example. So if you have a delayed computation which needs to be computed lazily, it's called a thunk. And if the garbage collector goes over the heap and it finds thunks that are easy to reduce, it just does that during garbage collection, and it gives us like a 10% performance boost. And if you try to implement a lazy language on top of a different runtime system, for example, some common runtime like the Java abstract machine, then the Java virtual machine, then you end up losing performance because they don't have those facilities for lazy evaluation. And that's why, for example, Scala, it doesn't have lazy evaluation, and if it did, it would be much slower. And same goes for tail recursion. So it's because of the way that the Haskell stack works, which is different from a normal stack. Tail recursion is basically free, which isn't true in other languages where you have to use trampolining. So it's just that there are many small details that add up, and as the result you get something that actually can be used in practice as opposed to a theoretical toy, which is what you are more likely to end up with if you approach lazy evaluation naively.
Wow, that's what is trampolining you mentioned? I have I've never heard that term.
It's a technique how you could do something in library code to speed up your recursion somehow and do tail recursion, but it's got unpleasant constant factors. And I've never actually had to use it, because when I'm in a language that, I try to stay within the paradigm. If I'm writing a language that makes it difficult to write functional code, I will write imperative code. So if it requires trampolining, I will just avoid recursion and write a loop.
Gotcha. Wow, that's incredible. Is there anything in particular that you think Haskell gets kind of wrong, or at least frustrates you somehow?
That is a very challenging question to answer, because I don't know what's right and wrong when it comes to language design. I only can identify blatant flaws, like this obviously could be better. So I think that the design space for languages is huge. You can be lazy, you can be strict, you can be imperative, you can be declarative, functional, whatever. The terms are actually quite blurry. Sometimes you can mix those two, but still there is a lot of variation. You can be statically typed or dynamically typed, and every time like you make this decision, it's better for some use cases, worse for other use cases, a lot of trade-offs involved. And Haskell just occupies this niche of strongly typed functional programming that I personally tend to like. And when you're asking me what Haskell got wrong, I couldn't say that it's made some wrong choices, but for example, the choices that it did make, some of them could have been done better. So for instance, metaprogramming in Haskell in the form of template Haskell, I think it's not as well-rounded as metaprogramming in other languages. So there are ideas we could steal. Type-level programming, for example, when you look at the way it's done in Haskell, yes, it can be done, but then you look at the way it's done in languages that take type-level programming more seriously, like the proof assistants that we are likely to talk about in this interview as well, then they have such a holistic approach to everything. Like they don't separate the type language from the term language. It's all a single language that works at both levels. And I'm thinking, yeah, this is a much nicer way to do the same thing that Haskell is doing. So for every design choice, there are worse and better ways to achieve the stated goals and to implement this design in the language. But I wouldn't judge a language for making a design choice that is different, because it might be dictated by other constraints that are just not relatable to me, not relatable to the work I'm doing. Because I'm interested in writing compilers, right? And somebody working on real-time systems, on hardware, has a very different view on what they need in their language. And I wouldn't be going to them and saying, you know what, you're doing everything wrong. This is how you should be doing programming. This is how you should be doing like designing your programming language and stuff like that. No, they have their area of expertise. I have things that I work on and where I have like this rough idea of how things need to be done. And my ideas of what's right is what led me to using Haskell. So for me, everything in Haskell is very good. Like, I've chosen this language because it fits my view of what's right.
That's awesome. I love it. Very considerate as well of the work a lot of people has been putting on different things, right? Haskell, I think it's one of my first functional programming languages, and it really is very beautiful. It's really, really beautiful. But personally speaking, one thing that frustrates me in Haskell, it's the not necessarily the module system, but Cabal. How's it called? Like the package management system. I think it's just a little too wonky to use still. We could be doing better. I think it's better than when I started using. Like, it had great improvements, but when I go back, I still struggle a little bit. Maybe I'm just a little dumb to use it, but I feel like things should be better.
There is the old Cabal that installed everything globally.
Right. Yep.
Then they've introduced sandboxes, so you could specify a directory per project and install libraries for every project individually. But you still had to do it manually. And then came along Stack, which did exactly that. It created a directory per project, but also it used a sharing system. So if you have multiple projects using the same library, this one would be cached globally. And after that, we got the new Cabal, which actually got inspiration from Nix. And it uses, I think it's content addressable storage or something like that, but basically it's a pure form of storage. So whenever you build a library, it's saved in this global cache, but it doesn't conflict with any others, and you still get a separate build plan per project for all your libraries, and there is no problem that was previously called Cabal hell, when you couldn't install multiple libraries, when you could install multiple versions of the same library in your system because it was all stored globally. But now it's this global store without conflicts. And honestly, I don't know how it could be done better. I mean, isn't it the solution to the problem of installing dependencies? I'm not sure. I know that Carga in Rust gets a lot of praise. Do you know if they're doing anything different which gives them the reputation that is so much better? Because when I compare the two tools, they seem to be doing very similar things.
Well, I don't know. Like, all the times that I've had to use Cargo, for example, things just work. Like, I just do Cargo whatever, and it doesn't, like, it's rare for it to give me some error that I have to tweak. And sometimes when the problems I face in Haskell, they're really hard to read as well, especially in the dependency system. So I don't know. It's just, as I said, maybe I don't have the proper mindset of how to use it properly either. I don't know. But also, it's been a while. I don't use. Maybe, as you said, like, there is a new version of Cabal as well. But I don't know. One thing that I'll give you one last argument though. Like, the first comer, when it comes into a Haskell project, you already have to choose whether you use Cabal or Stack, and it's not very clear which one and why. And then you immediately already have to understand a lot of technicality to do that choice. And I think that makes things harder a little bit to use. But it's just some thoughts.
Yes, I think it was a very unfortunate ecosystem split that we've got Stack as a separate build tool. It was born out of real frustration with Cabal, but as I've mentioned, the Cabal has changed as well. So it's like the timeline is like this: old Cabal, Stack appears, new Cabal. And currently, I would recommend the new Cabal, like the one you get out of the box when you install Cabal.
Maybe I should try again and come back to see what is the difference now. Maybe solved all my frustrations already.
I get no problems with the new Cabal. It's still a little bit rough around the edges. So, for example, the directory that it puts the build artifacts into is called dist new style. What the hell is new style? Well, that's because it's the new Cabal. As any tool that is developed by volunteers, an open source tool, you will always find some small bugs and annoyances, and you start to dig into it, and you're asking yourself, why would anybody do it this way? And in the end, it turns out that nobody just had the time to address it. Like, everybody knows, they just don't have the time to address it. Maybe who if not you, right? And that gives me peace of mind whenever I dislike something in the tools that I use. I don't get the mindset of, oh, it's so bad, I wish it would be better. I'm more like, I wish I had the time to fix that, but I have to pick my battles.
That's a very nice, very important insight too, because this is what makes Haskell so unique, right? Like it's actually impressive that Haskell actually works the way it is made of, right? Because it's completely volunteer, born out of as a research endeavor from many different thought leaders in the programming language community. It's actually impressive that it's actually an industry level language, really. And all these things that maybe we usually the things that we kind of find fault or complain about Haskell, it's exactly because of that, because there is now there is Haskell Foundation to steer the development somehow, but still the Haskell Foundation is made entirely out of volunteers, and many of those volunteers have, as you mentioned before, they have different backgrounds and different ideas of what is beautiful or what's important to work on, right? So there's like, for example, Rust was born out of Mozilla Foundation, if I remember correctly. So there is this, from the get-go, there is this it was unified, the vision of where this language should go and how it should be done, right? Like, so it's much easier to get something polished, that the features are polished to work in a particular way. And that's just not how Haskell is conceived, right? Like, Haskell is conceived to take in different ideas from different people, from different backgrounds, and that makes the language a lot more beautiful. Like, it's but much more things, right? And with a lot more space to try different things and try new things, which is really, really cool. Makes Haskell is really a very unique language in that sense.
Yeah, one thing that I think should be stated explicitly is that the GHC Steering Committee and the Haskell Foundation are two different structures. So what I was describing about volunteers with different backgrounds, they're the GHC Steering Committees, and you can think of the GHC Steering Committee as a pure function from string to bool. You give them the proposal and they tell you if it's accepted or not. And well, sometimes they also give you useful feedback, but that's not the main goal. The main goal is to determine what goes into the language and what doesn't. And the Haskell Foundation is very different. I'm not sure if it's volunteer-based. I think there are positions at the Haskell Foundation, and it doesn't only determine what goes in and what doesn't, but actually invest into the development of the things that need to happen, which are related to infrastructure and the ecosystem and related stuff, so that everything goes smoothly around Haskell, because there is more than just contemplating, oh, that would be good and that wouldn't be good, and here are the technical reasons. That's what the steering committee does, and the Haskell Foundation is focused on the more practical side of things.
Okay, well, thank you for the explanation. That does illuminate things better.
Yes, and when it comes to actually doing the implementation work, you're right that it's often volunteers doing that, sometimes funded by the Haskell Foundation, sometimes funded by commercial organizations, like Serokell funds my work. I know that other companies fund work on the backends, for example, the JavaScript backend and the WASM backend for GHC. Linear types, another very exciting type system extension, was also funded by a commercial company. And sometimes it's universities, so they let their students work through their idea, and it's nice to write in your paper that it's been put into practice by implementing it in a production-grade compiler. Right? So there are very different structures, and people are incentivized differently why they contribute to Haskell, which I think is a very good thing for Haskell, that it doesn't represent the interests of any one particular company, and it's not biased towards the interests of any one particular company, but it's a huge community effort. Many people with very different backgrounds contribute to GHC, and I'm looking at the commit history, for example. We get an average of 4 commits a day from very different people.
That's crazy. That's incredible. And how does the, let's talk a little bit more about the GHC itself. Like you're talking about this commits that you're talking about. I assume you're saying that the GHC takes this in average 4 commits a day, right? How does the code base actually look like? How hard would you say it would be for someone that never opened, like has Haskell background, knows a lot of Haskell, but never touched the GHC? How hard would it be for him to contribute somehow?
Okay, I think it's not hard. When you look back at it, you will think it's not hard, but it is intimidating at first. So the GHC code base is 300,000 lines of code, and that's just code, and 200,000 lines of comments.
Oh.
Yes, so there is almost as much comments as code. And it's organized in a very neat system called notes. So you write a few paragraphs explaining the general concept of what's being implemented, or maybe some intricate technical details that take a few paragraphs to explain, and then you mention this note identified by its title from various parts of code, and sometimes multiple parts of code will reference the same note, and you're reading code, you see just the code, but every couple of lines you see a reference. See note about this and that. See note about this and that. See note about this and that. And when you struggle to understand the code, you scroll to the note and you read the high-level explanation of what's going on in that code, or maybe an explanation of why something is done a certain way. And it's a very well-documented code base. Sometimes those notes are stale, a little bit out of date, but typically you can figure out what it's talking about and, of course, update it while you're at it. So it's a very well documented code base. It's also accompanied with reasonable test coverage. So there are 10,000 tests in the test suite, and once you do an edit to the compiler, you can rebuild it, rerun the test suite, and most likely some tests will fail, and it will teach you a lot about the effects of the change that you've introduced into the language. Anytime a ticket is closed, a bug fix, for example, is introduced into the language, there is a regression test for that ticket. And when you're implementing a new feature, especially now with the proposal process, it is customary to do test coverage based on the examples in the proposal and on various corner cases in the specification. So that's also covered by tests. And what it takes for somebody who is new to compiler development to contribute to GHC, I think the first thing I would recommend is just get it built on your system. Clone the repo, build the compiler. Now you have your own compiler. You can do very small, insignificant changes, like change some small syntactic element. It doesn't need to be anything fancy. Change a comma to some Unicode symbol, to implement Unicode commas, right? It would be like a one character change in the lexer. But now you've got your own flavor of GC, and now you can start tinkering with it. The components that are easiest to start the work on are probably the front end, because you can immediately see how the set of strings that the compiler accepts is changing. So you could tweak the lexer, tweak the parser, accept a different set of programs. You don't even have to handle those new programs, like just put a padding there, put an undefined, but now the syntax is recognized by the compiler. You've added something to the language. Once you've got the parser part done, there are different components to the compiler. So you've got the lexer and the parser, then the renamer, which does name resolution, and it assigns a unique identifier to every string identifier. So if you've got two lambdas in your program and both of them are lambda x, obviously those are two different x's, and that's why they will get different unique identifiers. And at each use site, you will know which binder is being referenced. So assigning those numbers, unique numbers, to every identifier is what the name resolution component does. Then it does dependency analysis, which rearranges the declarations in the module in the appropriate order for type checking. So in Haskell we can write declarations in arbitrary order, but type checking requires that declarations that are being referenced have already been type checked previously, so they need to be in the correct orders. That's what dependency analysis does. It also identifies the strongly connected components, so if you have mutually recursive declarations, they will be put into a single group. Then the type checker handles those groups, and the type checker, it's got the bidirectional component, so it operates either in the checking mode or the inference mode. In the checking mode, you already know the type and you want to see that some piece of code satisfies that type. In inference mode, you don't know the type yet, you're figuring it out. And there is a constraint solver factored out separately. That's like a separate constraint solving engine that the type checker hooks into. After type checking, you do zonking, and zonking is basically making sure that you don't have any leftover intermediate structures introduced by the type checker. So the type checker, it records some intermediate information into pieces called meta variables. And after zonking, you have none of those left. So it's just cleaning up after the type checker. And once you've zonked your program, you get to the desugarer, which translates it from the Haskell language to the GHC Core language. That was the front end of the compiler, and if you're starting to do something with Haskell, like introducing a new feature, that's the easiest part, where you could like make small changes and see what breaks, because the front end handles the programs that the user has written. The core language is a small calculus with I don't remember how many exactly, but about 10 constructors. So Haskell has hundreds of syntactic constructs. In the core language, there are about 10. And this is like the sort of language that you would publish in a paper. It's very small, very well defined, has its own type checker, which is separate from the Haskell type checker. The core's type checker is called lint, core lint, and it's there just for debugging the compiler itself, because if the front end is correct, then it will produce a type correct core program. So the core program, it undergoes some optimizations. So the core of the compiler, it transforms core to core. You start with a core program produced by the front end, and you transform it until it turns into something that could be reasonably fed into the backend, something with better performance characteristics. In the backend, it goes core into STG, into CMM, into native code generation. That's the part that I haven't worked on much, but somebody more inclined to tinker with low-level stuff will find a lot of interesting technology there. Yes, so that's like the overview of the Haskell pipeline. And previously, GHC used a flat module structure, so the modules were all around the place. You couldn't figure out what was part of which component. But there was an effort, a very concerted effort, to actually use hierarchical module names. So when I started working on GHC, the modules were a mess, but now it's very well organized into those components, and you can just decide what you want to work on, and you will find the relevant modules.
Wow, that was a crash course on the GHC. That was incredible. Thank you so much for sharing that. Do you know on the top of your mind what are those 10 constructors you mentioned on GHC Core? Just so we can have a better idea. It's okay if you don't, though.
Well, let me try. I think you will have constants, so literals. You will have variables and variable binders, so lambdas. You will have function application. So that's just the core lambda calculus. Applications will be either term applications or type applications.
Right. So type binders
for
as well?
Type applications, yes, and type binders. Yes, that's right. There will be let, and let in core corresponds to allocation. So you see a let, that means that in the resulting code there will be an allocation for that variable. And there is a case. A case forces the scrutiny before you can pattern match on it. So you see a case, you know there will be evaluation. So core has a more or less direct computational interpretation. Let allocates and case reduces.
So case is for ADT, so also constructor for ADT maybe?
You don't declare the ADTs in core. They're just so they're just part of the ambient environment, but you only operate on term level expressions, assuming the ADTs are just there. Yes, when you pattern match on the ADTs in core, you do pattern matching only one constructor deep, so you don't do multiple branches. I mean, no, you're not doing multiple arguments at the same time, like you do with pattern matching in Haskell functions, and you don't do nested pattern matching. So every layer of pattern matching and every argument of pattern matching will be a separate case constructor. And then to make it all work with gadgets and type families and stuff like that, we've got coercions. And coercions are basically breadcrumbs left by the type checker, by the complex type checker for the surface language, so that the simple type checker of core, called core lint, could follow those breadcrumbs and actually verify that the types are correct.
Okay, yeah, very, very simple. And so I assume then you come up with coercions for JGTs and type classes once that is taken care of, right?
For type classes, you don't get coercions. You get coercions are for equality constraints. All other type classes get.
You don't get it for type classes?
For type classes, we get dictionaries.
Okay.
And dictionaries are just regular values. So every type class, the class declaration is like a record type where every class method is a record field. So you declare a class with 5 methods, that's a record with 5 fields. And every instance of that class is a value of that record that contains the implementations for those methods.
But then those records, they can be they can take type parameters just like JDTs, right? That's what I was having in mind. So there can also have some kind of resolution there, right?
Yes, but finding the instances depending on the type parameters is part of the constraint solver, and it doesn't matter how you found that instance. As soon as you found it, it's just a reference to that particular instance as if you have written it explicitly. What we leave the breadcrumbs for is how we've solved the equality constraints. So when we have a type family, for example, and we've proved that f of int is bool, but we've done that by going through 5 intermediate steps of transforming one type into another, that also required a lot of effort on constraint solving. But you see, if you make a mistake and somehow put a wrong type class instance, that doesn't give you a segfault at runtime. That just means you've got a different instance. But so that's not a soundness issue. But if you've somehow proved that int equals bool, that is a soundness issue. So you better leave those breadcrumbs for all your reasoning with equality constraints. That's what the coercions are for.
Okay, gotcha. Thank you. Cool. Okay. Anything else you wanted to mention about the JGC?
Well, let me think. And the question was how to contribute to GHC. My suggestion was to just download it and start hacking. Oh, yes. You probably should go to the issue tracker and search for the newcomer label, because there will be, if you already have an idea of what you want to implement in it, yeah, just it's nice. You can go ahead and do your idea. But if you just have this vague feeling of I need to be doing compiler development, but you don't know exactly what you want to be doing, then there's this newcomer label, and you will find tickets. Hopefully one of them will be something that you might be interested in working.
Yeah, newcomers labels are always a great place to start in any project.
Yeah, I wish there were more of them. Like sometimes you have to search for keywords before you realize that when you're looking for something to do in GHC, one way is to use the newcomer label. The other one is to search for keywords related to your area of interest. And sometimes you find a ticket that could have had a newcomer label, but doesn't. So not all of them are comprehensively covered, but some of them are, and often those take just maybe a week to handle. So you put in a week of effort and you have a merge request, and then your name is forever in the commit history.
Yeah, that looks really good for a newcomer CV, like someone who's just starting their career. That would be really, really cool. And one thing I was going to mention is that this kind of stuff that we're talking about, like looking for the first time in a huge code base, and like maybe navigating, trying to find a simple issue. I personally think that's actually a pretty good application of LLMs. LLMs are really good at like looking at a lot of that big data that we have no idea how to work with, and like point on smaller things. Like even that thing you mentioned about how well commented the GHC is, I think like you could get a lot of help from LLMs when you feel like stuck. Hey, what is this thing here doing? LLMs are usually really good at compiling that kind of information. So I think developers nowadays, in that sense, like newcomers in that sense nowadays, have a lot of can get things a lot easier than when you first started or I first started, right? In that sense, you can get a lot of help.
Well, my general feeling is that LLMs are more useful on small projects, actually, because more of the project fits into the context window for the LLM, and its predictions are sometimes even insightful. For GHC, sometimes I try to get an LLM to do some work for me, and I have to guide it a lot. Like, no, you're going completely down the wrong path. This is not how it should be done. Look at that module. Look at this module. Look how it's done there. And then, I see now. Thank you for correcting me. So, unfortunately, for large projects, you still have to know what you're doing at least a little bit to guide the LLM, but it can do some routine tasks. Yes, I was very skeptical last year, but the LLMs have improved, and this year I'm dabbling with vibe coding some of my merge requests. So I'm never happy with the LLM output, but it's just nice to let it try, go get a cup of coffee, and sometimes the output is just good enough so I can build on top of it.
Nice. Okay. Cool. Yes, I've been using for smaller projects. So yeah, it's nice that you mentioned that. I'm not sure. Okay, so let's talk about Dependent Haskell. Let's start from the beginning. What exactly is Dependent Haskell?
All right, so Dependent Haskell, just broadly speaking, is the initiative to add dependent types to Haskell. And that breaks down into multiple components, multiple ideas. One of them, and this is the core idea, like everything is built around this core idea, is that we want dependent quantification. So we've got in Haskell the for all quantifier that introduces a type variable, but it is a type variable, and that means it doesn't exist at runtime, right? So it gets completely erased. We get full erasure of types in Haskell. And on the other hand, we have the function arrow, which introduces a value. And the value is retained at runtime, and that means you can do useful computation with it. You can pattern match on it using case, and in every branch of the case, you do different things. So what if we combine those two ideas and we get a quantifier that introduces a variable that could be used both in the type, and you can pattern match on it because it's retained at runtime. It's not necessarily a type like int or bool or string. It could be a value of that type. So it could be an actual int like 5 or 10. It could be the length of a list or something. But by quantifying over it with this special quantifier called pi, which is the dependent product type, you get some properties from the function arrow, as if you passed an int to your function. So at runtime, it's going to behave like a regular value, but at compile time, it behaves like a for all. So you get a name for that variable that you could reference later in your type. So for example, the classic example is the length indexed vector. So if you pass an integer that you parameterize over, then you can not only pattern match it at runtime and do different things for vectors of different sizes, but also you get to mention it in the type of the vector, and some operation like zipping two lists together, if you define it on vectors, you can require that those lists are the same size.
And that the return is twice as big, right? That's also another property you get for free.
If you are zipping, then the return type is the same length, but if you are concatenating, then the return type will be the n plus m length. Yes, so you get to prove various properties at compile time, and this is the keystone feature for any dependent type language, that you have this pi quantifier. Another thing is that this pi quantifier needs to quantify over something, and that brings us to the next topic, is type level data. So right now we have the data kind extension in Haskell, which allows you to promote ADTs, and we have special case support for characters, numbers, natural numbers, and strings. Just those three. But if you want to promote a function, you cannot. If you want to promote an unboxed type, you also cannot. Other numeric types like floating point numbers, you cannot promote those. IO actions you cannot promote. Vectors you cannot promote, and many other data types that you could use easily at the term level, you try to promote them, that doesn't work. So data kinds is limited in what it can handle. It can handle ADTs, but to write dependent type programs, we wouldn't want to deal with this restriction. We would prefer to promote everything. Most importantly functions, but just generally everything gets promoted. So type level data needs to be handled more thoroughly. And on the topic of promoting functions, now we are in the territory of type level computation. So what does it mean to promote a function, how it behaves at the type level, which semantics it has, how it's evaluated, that is, for example, different from type families, because type families as they exist are a set of equations that are applied in arbitrary order, so you don't know the asymptotics of your function if you encode it as a type family. It could be a linear type function, but because the type checker chooses an unfortunate order of reductions for its equations, will take quadratic time or worse. Quadratic function could become exponential, and that leads to terrible compile times. So now we need to figure out a way to do type level computation reliably and promote the functions. So those would be the three aspects to it. I think it's dependent quantification, relatedly dependent pattern matching. So when you do case analysis on those dependent variables, you get type refinement in each branch. Then you have type level data, and then computation on these type level data. And once we have all those pieces in the language, we can do useful correctness proving for our programs. So we could state some interesting theorems about how our code behaves and prove those theorems to the compiler, or we just get better expressivity.
That's a very, very complete explanation. Thank you. Very, very nice. So why do you think it would be a good idea to add dependent types to Haskell?
Because it's already there, but it's ugly and slow. So Haskell already has all the components I've listed. They're just bad. So we have data kinds for type level data, but as I've mentioned, not everything gets promoted with data kinds. So this needs to be fixed. Haskell has dependent pattern matching with GADs. So with GADs, or rather, it gets type refinement because every constructor may store equality constraints. And building on top of that, there is this notion of singleton types. You can simulate dependent quantification using singleton types. But then you need to bring in template Haskell to generate those singletons, and then you get the runtime overhead of converting between your normal data and singletonized data. So it's slow at compile time, it's slow at runtime, but it's there, it works. It just needs to be nice to be useful. And we get type level computation. As I've mentioned, type families don't get a predictable reduction order, so your functions that you encode as type families may be very unpredictably slow. Furthermore, you don't have partial application, so all your function calls need to be first order. These can be worked out with defunctionalization, and it also exists as a template Haskell helper in the singletons library, so it's also there. And if you're very stubborn and you're looking for trouble and you're brave enough, you get this library and you start dependently typed programming in Haskell, and you do prove theorems about your code, and it's really fun, really nice, until you get to do something substantial when you just hit the technical limits of the compiler not being able to handle this much complexity with those half-baked features. And I'm just trying to figure out a way to make it actually practical, not a toy. And there is a way. We know how to do it. We can see it in other dependent type languages. Of course, Haskell will get its own flavor of dependent types, which is somewhat different. But generally speaking, we are already equipped with capabilities for doing dependent type programming in Haskell. We would rather prefer better capabilities, which we are implementing now.
What are the major difficulties to implement this? Because you've been doing this for quite a while, right? More than 10 years, if I got it right?
Well, it's less than 10 years, but it has been a while. I think I've started in 2018, so that makes it 8 years. 8 years, yes, intermittently. Sometimes I took breaks, but yeah. And of course, I'm not spearheading this. So this is initially the work of Richard Eisenberg. I just thought I'd help a little bit, but Richard is now more active in the OCaml ecosystem, and he's doing some very impressive work, but it's OCaml work. And now I have to...
He was a PhD student of Stephanie Warish, if I remember correctly, right? He was one of the main first people thinking about dependent Haskell, I remember. But then I think she's not interested in that anymore. I don't know.
Of course, they're all interested in that, but they have to go on and do new research. And it's just very time-consuming engineering work to actually finish it in the compiler. So because I think the ideas are so good, I just have to step up. And I'm very lucky that I also convinced the company that it's a worthwhile initiative.
So you're saying that the technical details is done, like the proof, the pen and paper part of the engineering, like the thoughts.
Well, it doesn't handle the... so obviously it does some simplification. So it doesn't explain everything. It takes a subset of Haskell that could be reasonably dealt with in the paper. But generally speaking, most technical details are settled. So if you read Richard's PhD thesis, which is called Dependent Types in Haskell Theory and Practice, I think, it presents like a surface language with dependent types, a core language with dependent types, and a way to elaborate the surface language into the core language. It settles almost all design choices of how it should be done, which align with what could be implemented in Haskell practically. And after that, there's also a paper published called Systemd, which introduces Systemd and Systemdc, which is D for dependent types, I think, and C for coercions, which shows how the Haskell core could be extended to handle dependent types. So we've got a very good framework of how to think about extending the surface language, a good framework to think about how to extend the core language, and also some idea of how to do the elaboration between the two to make it feasible in practice. What's left is actually doing it and handling the corner cases and technical details, and there are a lot, because Haskell is a language with long history. It's not an academic language. It's a commercially used language, has been around for many years. You cannot do changes willy-nilly. You have to care about backwards compatibility, slowly transitioning the ecosystem, and not degrading performance, stuff like that. So the two main areas of work are extending the surface language, which eventually ends up breaking code anyway. We're just trying to find ways to do it less. So we're trying to do as little breakage as possible while we're introducing dependent types. But for example, we had to steal the for all keyword, right? Previously, you could use for all as the name of your variables. Now you cannot, so it's a reserved keyword. And that caused breakage, and people complained, but we had to do it. And on the other side, we've got the core language that I talked about, the GHC Core, which also needs to change. And that, because it's such a central component of the compiler, changing it is not easy. And you have to update every optimization pass to handle the extended language. And if you don't update the optimizer appropriately, you will start seeing performance degradation in the runtime of the programs that you're compiling. So that is not acceptable, and it will take a lot of very careful work to update this core language to use Systemd. And in parallel to that, there are other features being developed for Haskell, like linear types, which also require updating core. So they've got usage tracking, I think, for linearity, or I might be getting the details wrong, but they're tracking for every variable if it's linear or not, and they also can assign a variable multiplicity, which is instantiated later at use sites. And the problem is that there is no paper that would combine their model of linearity with the model of dependent types in the Systemd paper. Then Richard published a paper that combined those partially without handling the multiplicity polymorphism. So we've now got a set of papers that so we've got the PhD thesis that lays out the big picture. We've got the Systemd paper that shows how the core needs to be updated. We've got a slightly different version that also explains how to update it to work nicely together with linear types based on QTT. And by the time it's implemented in GHC, I think we will need to do more and more and more. Like it's the backlog grows as we delve deeper into it. Like it's a fractal of complexity. You fix one thing, you discover that it gives rise to 3 more small things that need to be handled. And sometimes handling those smaller things requires a GHC proposal, which ends up being discussed for 2 years before you can act on it. And it's such a slow process, which is why we don't have dependent types yet. But we're making progress very steadily. Like it's very slow, but it's very steady. We're not stalled or anything. It's just that we need to do this and then that and then that. And I have like a graph of tasks that need to be completed before we can declare victory.
Let's talk about the set of tasks that you're mentioning. I'll ask the editor to put it on the video version of the episode for those watching that, but those who are just listening, they can follow along as well.
Yeah, that's right. So I've got this graph that I've published to reduce the buzz factor because I've realized at some point that it was mostly Richard working on Dependent Haskell. Then I've started to help, and it was Richard with a little bit of my help, and currently it's mostly me doing this work and holding everything in my head of what needs to be done. And it would be really nice if other people could join and do their small contribution, which is why I published this graph, and I tried to break it up into small tasks, which there are about 50. Right, about 50 tasks. The graph, by the way, I don't think it's in its final form, and it will grow over time as some of those tasks turn out to be one task may turn out to be 5 tasks in disguise. So once we start doing it, we will have to break it into subtasks. But right now it's about 50. And the general picture is that we've got the cleanup tasks, like taking the existing Haskell features, identifying the obvious problems with those extensions, and before we try to add something new, let's fix the foundation that we're building upon. So some of those tasks are paying off either technical debt or design debt in the sense of language design. So some features should have been designed slightly differently. We're only now realizing how exactly, and that needs to be finished before we move on to adding dependent types. The cleanup tasks are nearly complete. So 8 years later, I think we are finally approaching the point where we are looking not at cleaning up the language, but actually adding new things into it.
Nice. Good.
Yes, so the things that needed to be introduced and which are complete now are unifying types and kinds, adding standalone kind signatures, adding type applications and type abstractions, dealing with syntactic issues like the tilde operator or the dot type operator, the for all keyword, dealing with punning of constructors, and allowing visible quantification of type variables. So the things that I've listed are done, so they're marked as complete in the task graph, and we're moving on now to, I think, hopefully next year I will try to tackle unsaturated type families. There is a nice paper about that, which would remove the need for defunctionalization. And defunctionalization, maybe I should say a few words about it. It's a technique for adding support for partial application in a system where partial application functions is not natively supported. So if you're trying to map over a list, right, you give a function f to map, but this function f takes a parameter, and in a first-class system, you just cannot do that. You cannot you cannot mention a function without giving it all of its parameters. And the fix is to introduce a symbol for every function, and instead of calling them directly, use a helper called apply. So apply takes a function symbol and the parameters for the arguments for that function and calls the function. But if you don't supply enough parameters, it gives you an intermediate representation which basically reifies the closure for that function directly and explicitly. And when you call apply another time, but this time you supply this closure to the left-hand side, it may either add yet another parameter or reduce. And with this encoding, you can add, for example, partial application to type families. And of course, you have to do it manually or with template Haskell, whether we would rather just not introduce this accidental complexity, we would rather support it directly in the language, which is why we would like to have unsaturated type families. And the way that unsaturated type families work, the way they are described in the paper, builds directly on the work in Richard's dissertation about dependent Haskell, which introduces two forms of arrows, the matchable and the unmatchable arrows, and making this distinction will allow us to retain reasonable type inference, because Haskell wouldn't be Haskell without its capabilities for type inference, and the type families and type synonyms cannot be partially applied because it would normally create issues for type inference. But if we introduce two notions of arrows, like arrows for injective and generative type constructors versus arrows for non-generative type constructors, then we can retain the properties that we need. And I think that that would be a natural next step. What could be tackled next? After that, we get to consider promoting more data types. So we can promote natural and strings, natural numbers and strings. We would like to promote, for example, classes, right? So class methods, and that means promoting dictionaries, and that means promoting constraints. All of that isn't part of Haskell right now. We should be adding that. And if we're promoting functions, that we should probably be promoting lambdas. So promoting lambdas would be another feature. If we promote lambdas, we need to evaluate them. And for that, I'd like to introduce an open term evaluator, which does normalization by evaluation, and a closed term evaluator, which hooks into the compiled form of the function for very fast evaluation. So that would be also nice to have.
Does that change? Like, obviously, it's changing the type checker, but if I remember correctly, having this dependent type stuff in the type level now, you start getting like undecidability of your type checking, no?
Yes, that's true. And a lot of that comes from higher order unification. So trying to infer the functions trying to fill unification variables with functions. And dependent Haskell, it simply doesn't attempt to do so. Whenever you get to this boundary where you start seeing these issues, it will require an explicit type annotation. So it will require more type annotations for code that relies heavily on dependent types. In exchange, it retains its very nice inference properties for simple code.
Gotcha. Okay. What about dependent pattern matching?
All right, so I'm just dependent pattern matching. That's something that we in some form already have. So pattern matching on a getted constructor it brings equalities into scope, which results in type refinement, which might be different in every branch of the case. We would just want to have that as a native construct of the core language, so that pattern matching on the value on any value could bring those equalities into scope, rather than the singletonized value with explicitly introduced equality constraints. Just a different take on something that already exists. So we have a pretty good idea of the moving parts. We just need to put them together.
This is what I was working on in my master thesis. That's why I always bring it up. For me, it's the nastiest part of dependent type languages. It's dependent pattern matching. They always look weird or wonky somehow, and things break, and it's hard to deal with.
Well, you might have a better idea than me of what it actually involves. I'm looking at, like, it does work, right? We have a practical implementation of that in Haskell today in the form of gadgets, and my thinking is entirely syntactic. Like, if we have this new construct, this is how we can think about it in terms of the existing one. If this new one, this is how we think about it in the terms of the existing one. And there are also papers with the core calculus. But I think that I'll actually better understand it once I get to implementing it. That's when I will cache in all the details. Right now, it's all paged out for me.
So you were saying that you were promoting type level lambdas, and then after that, then you finally get the dependent core language. Is that right?
Yeah, that's right. So cleaning up the language is nearly done. Then we are promoting all the data types with data kinds, more of them, including lambdas. And once we are promoting lambdas, so we have universal promotion for everything, we can move on to making the core language dependently typed and adding dependent products and dependent sums to the surface language. And that would mark the completion of the Dependent Haskell project. Things like totality checking aren't part of it, for instance.
The what? Sorry?
Totality checking, like making sure that your functions are not just pure but total, they terminate. Yeah, and if you want proof erasure, you need to prove totality of your functions. We're simply not doing proof erasure.
But that's also brings up another point as well, because if you do not have totality, then your proofs are basically unsound, right? Like you have no guarantee that the proof.
No, that's not exactly right. Your proofs are predicated on bringing them to normal form at runtime. So you evaluate your proof, you get it to a value, and and that gives you a proof term, but you have to actually run it at runtime.
But you have no guarantee that it will end, right? Like it might end up in a infinite loop, and then I see. I think I see the point.
Yeah. Yes, exactly. That's when you don't get your normal form, and that means your proof is wrong.
Okay. That's interesting. That's very interesting. I like it. Okay.
It's not strictly speaking like a compile time proof, because you do have to evaluate it at runtime. But if you prove int equals bool this way, then you don't get a seg fault. You get let's say an exception or a loop, right? So it's not as bad as a seg fault. So it's a proof, but a weaker version of a proof.
I don't know. I'm not sure if a loop is better than an exception. For me, it's worse, because then you don't know, right? Like
a loop is definitely worse than an exception. I agree with that, but it's better than a seg fault.
Okay. Fair enough. Okay.
So in a very technical sense, we're not compromising soundness here, right? So if you write a bad proof, we're still working with a sound system, but it may loop. Yeah.
So what other practical limitations would you get in Haskell dependent Haskell.
Yeah, I'd say no totality checking and no higher order unification are the two big ones that people coming from other dependently typed languages would be surprised to find that aren't there. That also means no proof erasure. On the other hand, it will integrate more nicely with it can be easily used with existing Haskell code. So we put a lot of effort into making sure that if you use dependent Haskell, then you can use existing libraries very easily. And if you write your own library with dependent Haskell, then your code will be easily callable from code that doesn't rely on dependent types. Making it work with the existing system is a huge part of the equation.
And also making sure that things will still be performant sounds really hard too, because proofs, like you said, that you're not going to have erasure of proofs, and proofs can have a huge burden as well. So yeah, curious how your guy is going to deal with that.
Unfortunately, there isn't a better answer than to write a rewrite rule, which is unsound. So once you've run your program enough times to build confidence that your proofs evaluate to normal form every time, you write a rewrite rule, fingers crossed, it's actually a sound proof, so let's not run it next time. So maybe you'll have two builds of your program, like the one with running the proofs that you can run it on, you can run it to diagnose nasty bugs, and the one you actually deploy to production that erases the proofs, even though it's unsound to erase them.
No, but it's very fair. I think it's very fair. There are some techniques. I'm not entirely sure about them, but there are some techniques to reason about rewrite rules. I think Jesper Cox started working on that in Agda. I think I'd be wrong. I have to check on that. Okay. Then we already talked about the major milestones and things that are hard. Yeah, I think we covered pretty much. Anything else we should talk about dependent Haskell?
Well, I'd like to bring up the latest milestone that has been implemented, which is the RequiredTypeArguments extension. And dependent Haskell, it introduces 12 quantifiers. So the existing quantifiers are for all and the function arrow and the constraint arrow. And dependent Haskell adds for each. Then for each and for all get two variations by having either a dot or an arrow after them, and that determines whether you supply the argument explicitly. And on top of that, every one of them can be either matchable or unmatchable, and that's how you get to the number of 12 quantifiers. And I'm quite proud to say that after all these years, I've implemented one more. So we have for all with an arrow, one of the quantifiers of dependent Haskell, which is like the regular for all, but you pass the type argument explicitly. And I think of it as laying the groundwork for each, because and for each is PyTypes, by the way. It's the name that we've picked for the dependent product. And the reason I think it's laying the groundwork for introducing for each later is that it deals with all the syntactic issues of using types and terms, which are two different sublanguages, together. So if you consider type applications, you prefix all your type applications with the @ sign. And that gives you a clear syntactic marker when to switch from term syntax to type syntax, which is something that we would like to avoid. We would like to pretend that terms and types are a single, just one unified language. So you don't have type level function application and term level function application. You just have function application. You don't have type literals and term literals. You just have literals. You don't have type variables and term variables. You just have variables. I mean, syntactically, we just want one single language. And it turned out that we actually don't have a single language in Haskell. The syntaxes were different. for example, the parser for the term level sublanguage treated the tilde always as a prefix operator for irrefutable pattern matches. So if you've ever written an irrefutable pattern match with there are the bang patterns with the exclamation mark and the irrefutable patterns with the tilde. So the term level parser was treating it this way. Then we've got the dot operator, which at the term level is either the actual dot operator for function composition or the field access syntax for the new record system. At the type level, it was very different. At the type level, you write a dot that was the dot from the for all, so it couldn't be used as a standalone operator. And the tilde that I've mentioned earlier, I forgot to compare it to the type level counterpart. At the type level, it was the equality operator. So a tilde b is the equality constraint. Right, at the term level, it was the irrefutable pattern match. So it turned out that those syntaxes were different, couldn't be combined. The most nasty one, like I really hated, but we had to find a way to deal with it, is view patterns. So do you remember the syntax for view patterns? It's a arrow b. It's a arrow b, and when you're pattern matching on a value, you're pattern matching. So let's say you write, like, picture this sequence of symbols in your mind. F applied to, in parentheses, a arrow b equals. So it looks like you're pattern matching on the function type, right? Yes, but you're not. You're actually applying the function a and pattern matching on the result with the pattern b. That's view patterns. So something that would very obviously be a match on the function arrow in the type family or in Dependent Haskell turns out is existing syntax for a completely different extension. And that had to be solved. So just nailing down all those little details, how to do this or how to do that, what we can break, what we should retain for backwards compatibility, solving those issues. It took so long. Oh, another one. How about the star syntax of kinds, like star, arrow, star? That's the kind of maybe, right? Star, arrow, star. But at the term level, the star gives you the multiplication operator.
Oh, right.
So you cannot write star, arrow, star. That's multiply, arrow, multiply.
Yes.
Yes, another one would be the promotion tick. So you write any name and you write like a single quote in front of it, like the tick, like tick A, for example. At the type level, that would be the data kind syntax for referencing the data namespace. At the term level, that's template Haskell syntax for quoting a name.
Yes. But wait, so what is the plan here? How do you deal with those things?
Yeah, so the idea is that we unify all those syntactic elements and then we resolve which one means what at the name resolution stage. So we needed to establish before the steering committee that we're not going to do this disambiguation at type checking phase. Like, we need it much early in the pipeline, and that makes the compiler dumber, which is good. And it took a long time to convince everybody that a dumb compiler is better than a smart compiler, because it's more predictable. And we've established the lexical scoping principle, which means that you should be able to figure out which construct means what without knowing the types in the context.
Oh, wow. That's bold.
Yes. So we went with this principle. We established a system that has this property. It's all described in the proposal that I wrote for visible for all and RequiredTypeArguments. And it's implemented in GHC now. So now that we have this feature and it's user-facing, users can supply type arguments to functions as if it's nothing. Like you call f of int. F could be, for example, size of, right? You would want the size of your data type in bits or bytes. I don't know. You could ask what's the size of int, the size of bool, the size of double in memory, and the function would give you that result. And previously you had to use workarounds like the proxy data type, so you wouldn't call size of int, you would call size of proxy int. And now you just can pass the type directly without any syntactic marker, and that required resolving all those syntactic issues. But the feature is there, and that means two things. The first thing is that we have this syntactic foundation for dependent types. So once we're introducing actual dependent types, we can focus on the semantics. The syntactic issues have been resolved. And the second thing is that I finally have an excuse to merge the internal representations in the compiler to represent types and terms using identical AST nodes. So this feature, having landed in Haskell, gives me the creative license to refactor half the compiler in the way that I see fit for dependent types.
Nice. Wow, that's a lot of work. Honestly, I think you're doing a much harder job than implementing a dependently typed language from scratch, because like you're trying to make sure that like you're adding dependent types on top of an already existing industry level language. It's so much work. So props to you. Great stuff, man.
Well, I'm doing my best, but I rely heavily on reviewers for my MRs to actually point me in the right direction. So I talk a lot with Simon and Sam and everybody else, and they give me really good ideas. And having the steering committee also helps. So the approaches that I come up with, they turn out to be bad before I waste time implementing them, because the committee thinks hard about them and tells me, you know what, this isn't the way to do it. And I'm reading their comments and I'm thinking, you're right, that's not the way to do it. I have to come up with better ideas. It's a very nice process. It just takes a long time, but I'm very happy with the results that it produces, because it's a very comprehensive approach. We're trying to do things right.
Nice. I really like it. I really appreciate it. Really appreciate all of your work and everyone in the steering committee and all the effort you guys put into it. So yeah, the name of all the users of Haskell. Thank you.
Yes, thank you. I'm hoping that I will finish it in my lifetime. I have another feature that I wanted to talk about, and it's dependency analysis. So Haskell needs to rearrange the declarations in a module in the right order before it can type check them. And it took many years to figure out how to do it that would work reliably. And the solution that we found is so bad that it's good.
What?
Yes, because we've tried to do smart things. None of the smart things worked, and we did the stupid thing, and the stupid thing worked. I'll tell you how. So we thought that we would build a graph where the declarations are nodes and the arrows are dependencies, and then according to this graph we would do a topological sort, putting the nodes in the right order, because that's how it's always been done in GHC, except we needed to figure out a way how to draw arrows between type instances for type families. Because the problem is that most things that you use in your declaration are explicit. So you refer to another data type. You declare a data type whose field. So let's say you're declaring a record R, and this record has fields A and B with types capital A, capital B. obviously, this record declaration depends on data types capital A, capital B, right? So they need to already have been added to the context for your declaration to make sense. And that's when we draw an arrow on the graph from R to A and from R to B. And that's how we build the graph. But sometimes you need an instance of a type family, which once reduced gives you the necessary knowledge to type check your declaration. So let's say you're declaring a type synonym, and in this type synonym you use something whose kind mentions a type family applied to another type, and this kind needs to reduce for to unify with the kind of the type synonym. It's a little bit convoluted, but the key point here is that there is a type family occurring in the kind, and we need to reduce it for kind checking to succeed. Now, it turns out that you depend not just on the type family, which is easy to discover, but also on some of its instances which are needed to reduce in this particular context, and you don't know which instances. So we've got this idea that whenever you depend on the type family, you also depend on all of its instances. That should give us a good enough approximation, but it turns out that instances may depend on other instances, and there is just no way to discover how exactly. And it gets more complicated when the instances come from multiple modules. We've been trying to design a system of heuristics that would produce the correct dependency graph. And whenever we tried to implement this set of heuristics, we ran it on actual code and discovered that there is some corner case that isn't being handled by those heuristics, and we don't find the necessary declarations in the context. And it took many iterations, many years with implementing those failing heuristics. What we did in the end is this. We build a wrong graph. We know it's wrong. It doesn't handle type instances at all. In programs that don't have those type instances, the graph is correct. So in all programs that already exist out there, the Haskell programs that have been accepted by GHC before, they continue to work. The new programs, which hit the nasty corner cases that we're dealing with, we are adding a recovery mechanism. So when we cannot check some type declaration, it fails with an error, we set it aside and continue as if nothing happened. Go through the module, linearized according to the wrong graph, and whenever something fails, just set it aside. And by the time you're done, maybe you have that half of the module was set aside because you didn't have the right instance. But now you have it, and you can do another pass. And maybe some of them will succeed, some will not, and you do another pass, and then another pass, and then another pass, until you're either left with no declarations that are postponed, or you discover that you are not making any progress. And if you're not making any progress, then you're done. You give the error to the user. And if you've made progress, then it's at worst case, it's quadratic. If all your declarations are in reverse order, so you succeed with the last one, then the one before that, then the one before that, worst case is quadratic. In most practical examples, it's just 2 or 3 passes and we're done.
Yeah, that's very smart. Cool. Very cool.
I absolutely hate that it's so simple, because there was this mental block that we should do it before type checking.
Right. Yeah.
Right. We should build this graph. The question was, how do we build this graph? How do we discover the edges? And the solution was we cannot do that. Let's just do a retrying mechanism.
It's kind of like a saturation algorithm, right? Like you're just adding more information slowly. Pretty cool.
Yes. What bothers me about this is that it's potentially expensive. It's quadratic, but the constant factors is that we're retype checking the same declarations over and over. And type checking a declaration might take a while. It requires constraint solving, and we're not remembering any intermediate results that we could reuse between those passes. So that might be a problem in pathological cases, and it could lead to suboptimal compile times. But it's better to have a slow thing that works and then make it fast later than like beat your head against the wall, not knowing what to do whatsoever.
Yeah, for sure. Absolutely. But talking about type level constraints, it made me think of universes in Dependent Haskell, because Haskell have kinds, but usually dependently typed languages have a whole hierarchy of universes. So it's like you have terms, you have types, and then you have types of types, and you have types of types, right? How do you deal with that in Dependent Haskell? Do you stop in kinds and don't go further?
So the reason we don't have to do that is that we run our proofs, because this universe hierarchy, it exists to solve the paradox that you can construct, you can cheat the totality checker with it. You can construct a proof term that loops, therefore it's not a correct proof term, and proof erasure becomes incorrect. So in order to avoid this paradox, I think it's called the Girard paradox, you have to introduce this stratified system of universes. And in Haskell we have exceptions. We have undefined, we have unrestricted recursion. Why not add type and type into the mix? just type and type doesn't make things much worse. We already have to run our proofs. And most likely nobody will ever hit this paradox, but if they do, we didn't make any promises that they wouldn't. Which is why I think it's going to be actually a much simpler system, right? If you're writing Dependent Haskell, you don't have to think about universes. There aren't any. You have type has kind type. That's it. End of story.
Cool. Yeah. Because of the running, it solves the issue. I like it. Good stuff. And yeah, if you need, and in the end of the day, like there is a difference in the, if I understand it correctly, there is a difference in the motivation behind Dependent Haskell as in the motivation of having a proof assistant, right? And Dependent Haskell is more to give you more power in the static, like on the kind of things that you can, the kind of properties that you can have statically. Not necessarily, like you're not hugely concerned about actually doing proofs of your programs, although it's nice to have proofs, right? But the more important part is to have a very strong, usable type system to encode strong variants on your programs, right?
Yes, and I think that in many applications, running the proofs is all right. You can actually do that. For example, if you're designing a DSL and you want to piggyback on Haskell's type checker, so the type system of your DSL is a restricted version of the Haskell's type system, so then running the proofs is running the type checking for your language. Of course you need to run the proofs for your language. And then another use case that which actually led me down the path of researching dependent types, which is why I personally am familiar with the topic, is that I was trying to create a library for abstract data descriptions. Like you have a value that says there is such an enum, such a record, such a tuple, such a list here and there and there. Like for example, JSON schema. right? JSON schema could be an example of that. So my JSON data has this structure. Or it could be a binary data format, like my binary format has this data structure. And this description has to come in at runtime. The description comes in at runtime, but also the value comes in at runtime. And that is a clear example of dependency, because the structure of the actual value depends on the value of the description. And working with this description, working with this value means that you also have to have this description that you pattern match on to know which code path to choose. So you are proof relevant either way. Just the logic of your program is already proof relevant. You don't get proof erasure if you're doing this sort of programming. So you're not losing anything if the language doesn't support proof erasure, which I guess the point is, if you're writing the style of code that is already proof relevant, then you're not losing anything by not having proof erasure.
Yeah, absolutely, for sure. Well, we're about to reach 2 hours of episode. I think we've covered quite a good amount. Let me check here on the questions that we've talked about, if there's something particularly important that we should bring up. Well, maybe an interesting question is, what is your view on how long it's going to take for you to finish implementing Dependent Haskell?
I don't remember. Was it a joke about nuclear synthesis or what? That it's always 10 years away? Every 10 years, it's 10 years away. I don't know. I'm making progress. That's what I can say. New features are getting implemented. My initial estimate was 5 years. I thought I would be done in 5 years. We're now 8 years in. So 5 years was obviously wrong. I'll give you 10 years now, so maybe 15 years. I don't know. The momentum is there, but it takes time and effort. Also, if more people join in, I think that will also speed up the process, and people have joined in. So there was a volunteer who implemented the modifier syntax. It's on the graph, and it was like almost entirely without my involvement. I only made some very small suggestions on how to handle the parsing, but they did everything else, which was very nice. The no list tuple puns extension was sponsored by another company, so they've one of their developers did that. I guess I did some improvements on top of that, but mostly it's their work, so also done without my involvement. And that's why I have the task graph. So if anyone wants to get involved and just do their small part, I'm trying to put it out there, like what needs to be done, and it can happen sooner if somebody steps up.
Awesome. So there you go. If you're a listener and you're interested, make sure to go to the website, ghc.serokell.io, and you see the dependence graph over there, and it's a very, very well documented graph with the steps that has been completed and their work, and yeah, it's very well put. You can see that Vlad put some very, very good effort to welcome newcomers, and yeah, I hope this episode can help to bring at least someone that might be interested in this. And I'm sure that there are people that might be interested. I know a lot of students that they get very frightened by seeing a project as big as GHC, and it doesn't even cross their minds that they might be able to contribute with something. Although I do know a lot of extremely, extremely smart students that I'm very confident that they would. Just lacks a little bit of either prodding on the right direction, like someone to come in as we are doing right now and saying, "Hey, you would be able to. You should try," or being a little bit too humble and thinking that no, maybe it's a little way above my skills, right? So yeah, I'd be very glad if someone in this show would tackle that. Is there anything else that we didn't get the chance to talk about that you think would be important?
I think that about covers it.
Yeah, it was a great pleasure on my end to do this, and yeah, thank you for your work. Thank you for being here.
Yeah, thank you very much for having me. It was very nice to share my enthusiasm for dependent types in Haskell. I hope some people found it interesting.
I really liked how I think you were able to keep things, like to be. I think you were very skillful in being on the right level of abstraction. Like we were able. I personally felt that I was able to follow along the technicalities of what you're saying, although you were doing some quite technical explanations. But it wasn't too hard to keep the mental context. So I think you did a great job, and I appreciate it. Thank you.
All right. See you.
I hope you guys enjoyed this episode as much as I did recording. Every now and then we do an episode that is quite technical, quite serious, and quite deep. I hope you guys enjoyed. Because I try to keep balance on some episodes are going to be a lot less technical, more conversational and personal. Other episodes are going to be quite a mix of both, which is most of them, I believe. But some of them are going to be super deep and super oriented into the goal of understanding something very deep. And in this one was talking about the GHC and in particular about the dependent types and Haskell. I hope you guys enjoyed it. Let us know what are your thoughts. We always have the comment session open in Spotify, on Apple Podcasts, but particularly on YouTube. I think that's a very good resource for us to have conversations over there, to have comments, and for you guys to let us know what is going on. Please also feel free to give us some feedback on Discord. Join our Discord. Go to typetheoryforall.com, and there you see a link to the Discord over there. We have almost 600 people being quite active. We're always talking about something, giving feedback on what people are working on or how they should approach some things. We have some very smart people in the Discord, and I'm very happy with this community we are building. And honestly, I'll be completely entirely honest with you guys. I haven't been advertising super much the Discord because I'm loving it to be so small, so familiar, like just people who really are really excited about type theory, and we are starting to get to know one another, and I'm very happy with the community we are building. If you are enjoying this show, if you're enjoying the community, if you're enjoying these things, please consider becoming a Patreon. I'll ask the producer, the editor, actually, I'm the producer. I'm asking the editor to put here, somewhere here, maybe here. I don't know, somewhere, the names of the patrons. We have quite some patrons, and I'm very happy and excited about it. I kind of have a personal goal to have maybe a couple more $100 per month with patrons, so that I can invest even more of my time there. If you pledge at least $10 a month, then you get access to our very exclusive Type Theory Exists podcast, where it's basically I've been vlogging at least once a month. This month I released 2 episodes, and I start talking about what is going on my research side, and talking about the ideas that I have in my mind, and the plans and the conversations that I'm having. I really open my heart over there and talk as if I'm talking with some very close friend, because I know that if you're putting your money into the show, you believe in it, you understand what we're trying to build here, and I trust you that we are building this safe environment together, right? So if that's something that interests you, go to typetheoryforall.com, and there's a somewhere written Patreon over there, and you can join our incredible, amazing, beautiful community of patrons. And in the past, I've been using this time at the end of the episode to talk more about the behind the scenes, and that's now more to the side of of the patrons. So I already talked about a little more about the behind the scenes with Vlad here, how we reached out to one another, and about a little more about the planning of that episode. So make sure to check that out. And don't forget to follow us on Twitter, TT4all. I think it's x.com/TT4all. That's our handler, TT4all. And what else? I think that's it. And I love you guys, and I hope to see you again very, very soon. Take care.